All right, Unit 6, Forces, Notes page 6. We have separate videos for each page, pages 3, 4, and 5. Here's page 6. All right, we did the note already on elevators, but basically scales tell you your normal force. Bathroom scales. This scale tells you your normal force, not your weight. I think it tells you your weight. It tells you your weight if you use it properly. If you stand on it, don't touch the windowsill, don't have anybody push on you, just stand steady on there, then the normal force matches the weight, and so it looks the same as your weight. However, if that scale somehow is accelerating, if you're accelerating, if it's on an angle, you're going to get your normal force. You're not going to get your body weight. Okay. The other note, in an elevator, your weight never changes. Your body weight, how the earth is pulling on you. Yes, we did discuss that as you gain altitude, your weight decreases, but that's very insignificant on the level of the problems we're doing, and you would never notice that difference on this bathroom scale. But in an elevator, so if your weight doesn't change, what does change? Well, there are times during the ride you feel heavier and feel lighter. That feeling is actually reflected in what we call the normal force, and it is also reflected in the reading on the scale, which is telling you the normal force. So let's run a couple examples here. We have a 700 Newton rider in an elevator. Most of our problems, as you saw on the other pages, are along the ground. This one is a vertical problem. So here's the elevator car, and here's the 700 Newton rider. So what can we write about them? Well, that 700 Newton rider has a weight of none other than 700 newtons. So we know the weight. Is there a normal force on the rider? Absolutely. Be careful, normal force is a balancing force, so we don't yet know what it is. Friction, well, the friction would be between the rider and the elevator floor. And they're not actually trying to move across each other, so no friction to worry about. No springs involved. An external force, well, is there anything pushing on the rider other than the floor? The normal force? No, so that's out too. Now what they did say here is it's moving upward. Okay, so our velocity is up, that's nice. But it's at a constant velocity. Constant velocity is F net 0. Acceleration 0. Look at your picture. If the F net is 0, what must the normal force be? It must balance the weight. So it is exactly 700 newtons. In fact, how would you feel? The normal force actually tells you how you would feel. If you are 700 newtons and you get on a scale and it feels like 700 newtons, you would feel as usual. This is as you traverse the mid-floors on the ride. So you get in the lobby, you press floor 10. Not floors 1 and 2, but as you pass floor 4, 5, 6, the ride should feel very steady. In fact, you shouldn't feel like you're moving at all if it's a nice elevator. You may feel a little bit of rattle, but you don't feel the up-down motion because you are at constant velocity, you're at equilibrium, and all the forces are balanced. Your body weight feels as usual. Let's look at another scenario. We have a 75 kilogram rider. Here's the elevator. Here's the rider. We know the mass is 75 kilograms. That by itself is good, but not a vector. So we can immediately jump to the force, the weight. The weight is m times g, and that comes out to, I believe, 736 newtons, but we can round that to 2 sig figs. Let's call that 740 newton weight. Good. What else do we know? Well, just like before, in an elevator, the only other force you're dealing with is the normal force. Now, that's a balancing force, so we don't yet know its value. We don't know its magnitude. Let's leave that. Fg is done, no friction, no spring. Okay, so what we're going to worry about is the external, but we have to worry about the net force in order to get us that, external. The only thing we got to worry about is the normal, and we got to get the net force to get the normal. So, what do we know? Well, we know the acceleration is 2 meters per second squared down. Now, what we've done in the past is we've just went ahead and called that positive or negative. Like you read down, maybe you want to call down as negative or down as positive. It really doesn't matter. We call down positive, make it interesting. Why not? Find the F net. F net is m times a, which we've done, which is 75 times 2, which is 150 newtons. Now, what we said stuck on you, the Conjoined twin baseball players from Unit 5, page like 9, 10. F net and acceleration always point the same way. So if the net force is 150 newtons and the acceleration is down, the net force is 150 newtons down. Good. You can easily reason your way through this. The net force is 150 down. That means the summary, the overall from this picture, is more down than up. The downward force has to be bigger than the upward force. If the upward force were bigger, the net force would be up. If they're the same, the net force would be 0. If the net force is down, well then the FG is bigger. How much bigger? 150 newtons bigger. And so you really don't need a formal way of dealing with this, but the quick way there, FG 740, this is 150 less, 740 minus 150 is 590. So you get your normal force is 590. And as I was saying before, but if you want a more formal way to deal with this, you can say, well, the net force is just the combination of the normal and the weight. Well, the net force we know is 150. We called down positive equals the normal plus the weight is 740, and we called that's also down, that down positive. Subtract from both sides, and the normal force will be negative 590 newtons. Since we called down positive, this means 590 up. That's the normal. Okay, how would you feel? The normal force tells you how you would feel. If the normal force is less than the weight, which it is, you feel lighter. And this actually happens basically approaching or leaving the top floors. Now it kind of makes sense if you think about it. As you're going up toward the top floor, here's your blinking light diagram. You're moving at a constant velocity, floor 4, 5, 6, 7. And then as you get to 8, instead of going here, you actually slow down a bit so you don't go as far. And then 9, you slow down some more, and then 10, you stop. So your blinking light diagram goes from constant velocity and then squeezes together. Which way is it accelerating? Well, the acceleration is toward the bigger spaces. The acceleration is down. Now what about when you leave the top floor? Doesn't the blinking light look the same? You start out at 0, and then it speeds up, speeds up, speeds up, till it hits the desired speed and stays at a steady speed. So you're also accelerating down. In both cases, accelerating down means net force down, means smaller normal force, means you feel lighter. In fact, a nice way to remember this is the hotel analogy. You feel heavy in the lobby, whether you're going or coming, doesn't matter. Light in the penthouse. It's really as you approach, not in. Or as you leave, not in. Anyway, we did all these notes before, just in case you need to see them. When you feel heavy, light, the same. Okay, good.